So we're going to talk about work now. Now work is the amount of energy that is expended to displace an object by exerting a force on it. And note this word, it's the amount of energy that is expended to move an object from one location to another. So you push on an object, you're going to do work. Now an interesting thing by this, if you don't actually displace the object, if the object doesn't move, you haven't done any work. You can push with whatever force you want. No displacement equals no work. Be careful of that. There possibly could be a test question that deals with that idea. Now, mathematically, work is the integral of force dot, the dot product, dr. Now, so this would be the force, and this would be the displacement here, and this is something called the dot product between two vectors, the integral of that. Now, you're like, dot product, I haven't learned that. That's not a big deal. What that's simply saying is force times displacement if it's going in the exact same direction. If it's going two different directions, for example, up here with this box, notice the force is kind of angling up. Maybe there's a rope pulling it, but the displacement is coming this way, right? And so we have to get the two aligned, because the only part of the force that we care about is the force that actually causes the displacement. So if this force was pulling straight upwards, it would not be causing any of the displacement to the right, so the work done would be zero. It's the energy expended to displace the object, not just the energy you expend just for the heck of it. Work has to be productive in physics. Now, if you're confused by this, don't worry about this dot product. For us, it's all, whenever we're doing the integral, the dot product is going to drop away because it's always going to end up being in the same direction. We'll end up calling that the x-axis. Another definition of the dot product, if you're only looking for magnitude, is the two things multiplied by each other times cosine of the angle between them. So work is force times displacement, or F delta x, cosine theta, where theta is the angle between the force and the displacement. Note cosine of 90 here, if this was 90 degrees, that's the force pointing straight up. Cosine of 90 is 0, and so the work that you do would be 0. Now this integral up here is already kind of giving away something that we're going to be doing, because we learned that an integral is asking for the area under a curve. So if we were to graph out, for example, force and displacement, work is going to be the area under a curve, or area under a force displacement graph. So like that area. Or if we didn't have something, I mean this one is standard here, right? You can divide it right there and get two pieces. But if you had a function, right, the area under this curve measured down to the x-axis, if we were going between these 2 points, right, if those were our endpoints or our points of integration. Now, a simple problem over here, if we were just going to try to solve one straightforward, for example, I've got a weightlifter. He lifts up, it looks like 50 kilograms, 2 meters, and the force he lifts with is going to be straight up, so work equals force of lift times delta x, right, delta x cosine theta. And my theta here is going to be 0 because the force and the lift are identically aligned. Also, think about this. If he's going to lift it up with constant velocity, a free body diagram here, F lift going up, if he's going to lift it up at constant velocity, the force he lifts with is going to be equal to the force of gravity, right? And the two are going to be exactly balanced out if he's going up at constant velocity. So what I can say is the work this guy does is mg, that's the force of gravity, right? Maybe I should insert another line in here. Sorry for that. Work equals Fg delta x, cosine of 0 is 0. Well, that's work equals mg delta x, and so then we can just multiply that through. Work equals 50 was my mass, 9.81, the acceleration of gravity, and he lifted it up 2 meters. Which then, of course, gives me 981, 50 times 2, 100 times 9.81, 981, and I didn't mention this, unit for work, joules, the unit for work, or energy, because you learned that also, the unit for work and energy, joules, and so I'd come out with 981 joules, but it looks like I only have one significant figure, so I'd have to round that to 1,000 joules of work. Another thing that you should start noticing is a relationship we're going to learn in the next lesson here, that work is measured in joules. Well, interestingly enough, energy is measured in joules also, and work is the amount of energy that we expend, so there is a connection between work and energy that we're going to get to. All right, here's a quick example problem for us. I've got a man pushing a lawnmower here, 52-degree angle, and so he's applying a force downwards like this. So here that is on my free body diagram. And my question is, how much work is the guy doing if he moves this lawnmower 150 meters at a constant velocity? And I give you a coefficient of friction, 0.20. Now, work, if you remember, is force of push, or the force you're applying, the force that's trying to do the work, times the displacement that force causes, the displacement of the object, cosine theta. And so if you look at this, I know delta x, 150 meters. I know theta, he was pushing at an angle of 52 degrees. The problem is I don't know the force of push. So to figure out the force of push, I go through a simple Newton's second law problem. So I sum up my forces, gravity going down, normal force going up, friction going backwards, and force of push coming down at an angle, right? And so then I can divide that force of push into components like I did right here, sum up the forces in the x and the y. Now, I'm going to jump immediately to the x because of a realization. Check this out. The acceleration in the x-axis is 0, which then leaves me Fp cosine theta minus the force of friction equals 0. And I know what the force of friction is, right? I know force of friction has an equation, Fp cosine theta minus mu normal force equals 0. And so subtracting my mu normal force to the other side, Fp cosine theta is going to equal mu Fn. And looking at this, I know that what the theta is, although I'm actually not even going to have to plug that in. I'll show you that here in a minute. And I know what mu is. If I only knew what the normal force is, I could solve for my force of push, which is what I need to substitute in over here, because I know the other two. And so where do I go? Well, the y-axis, of course, because here's normal force, so I start working in the y-axis. Now, in the y-axis, we know the acceleration, because in the y-axis, this lawnmower isn't flying up in the air, isn't going down to the earth, so the acceleration is 0. Now looking at this, I realize this must be a system of equations, because notice normal force here, and it also has the force of push, the force the man is pushing with. There, I do know mass and I do know gravity, I do know theta, so here are the only two variables I don't know, and those exact same two variables exist over here in the x-axis, and if I can solve for force of push, I can substitute that in. So I'm going to just follow habits, even though it might be easier to solve for normal force in the x and plug in. I'm going to follow old habits. I'm going to solve for normal force in the y, and then substitute that into the x to solve for the force of push, which then can be substituted into my work equation. All right, so I went ahead, solved for normal force, substituted in. Notice I use parentheses whenever I'm substituting in, because that's mu times the entire normal force here, and that's what it is, the entire normal force. So I must use parentheses, which then shows me I'm going to have to distribute my mu. And now I gather like terms, so I'm going to move my mu Fp cosine, that should say sine here, typo, sine theta to the other side to get my Fp's together. Now my entire goal, and what I'm doing here, and purposefully working this in letter form instead of in number form, is I'm trying to get at this Fp, which is then going to be able to substitute in over there. So now I've got them gathered, I'm going to factor out an Fp that'll let me divide away all of the other stuff. Whenever I go ahead and plug in numbers, I come out with 192.75 newtons. Another note, you probably are going to want to use parentheses whenever entering things into the calculator. That way you don't end up accidentally making some mistakes in here. Now I know my force. That'll allow me to substitute in to solve for how much work it did. And whenever I solve all the way through, plugging in numbers and then rounding for significant figures, I was only allowed 2 because of what was given. 2 significant figures, 18,000 joules was how much work the person did. Now the second question, how much work was done by friction, is actually incredibly easy here, because we already know that the force that you're applying forward, the component, force of push cosine theta, this component must balance out the force of friction. So whenever I solve all the way through, and you can double check, plug in all the numbers, substitute in, figure out mu times normal forces, and plug that in for the force over here, you're going to come out with the exact same answer, just one critical thing. The force of friction is pointing back in the negative direction. So I'm going to have a negative force of friction times 150, and the angle between them would be 0. So the work done by friction is going to come out to be, while the exact same thing, it's going to be negative 1,800 joules, because we're traveling at constant velocity. Now I want to do a quick comparison problem where we're looking at what happens if you lift a box, this box right here, let's say, straight up the ramp versus, just straight up 1.5 meters versus going up a ramp 7.2 meters long. And I'm only using a conservative force. We're going to learn more about conservative, non-conservative forces. But conservative constant force, right, gravity, no friction in this problem. If friction were in here, then we'd have to do a few other things. We'd just include friction in our ramp, free body diagram, solve for FP, substitute in. But here's the point. Whenever you're going straight up, work is force times displacement cosine theta, but the cosine theta drops off because there is no angle between them. This was like the first problem that we did, right? And so that completely drops off. Cosine of 0 is 0. So now the force of push is the same thing as the force of gravity times delta x, or here I should say delta y, right? Well, now that translates Fg as mg, and my delta x or delta y is the height of the ramp. That equation looks very familiar. Now I've got mgh, right? And I come out with a work to lift something straight up, 1.5 meters, the height of that ramp, 370 joules. And my curiosity is, do I do more or less work as I push something up the length of that ramp? Now the length of the ramp is 7.2 meters. So then I set up a free body diagram for this. I got force push, by the way. Check that out. We're doing it at constant velocity. You got force of push going up this way, force of gravity coming down this way, and of course this way, components, Fg sine theta always goes down the ramp, Fg cosine theta always goes into the ramp, opposite normal force. I chose positives and negatives here, right? I chose down the ramp to be positive, and then I set up my equation, and all I'm dealing with right now is the y-axis. I don't even need the x-axis. The reason I need the x-axis is friction with normal force, but I don't have any friction. So Fp minus Fg sine theta equals ma. And since I'm going at constant velocity, I know this acceleration right here is 0, leaving me Fp minus, I'm going to go ahead and break Fg into mg sine theta equals 0. And now I can subtract that or add that over, so Fp equals mg sine theta. And as I start substituting in numbers, I realize, oh no, I don't have here my angle, but that's really not a big deal. I mean, notice that I'm given the hypotenuse and the height, so I can just come over here and opposite over hypotenuse is sine, so sine theta is going to end up equaling opposite 1.5 over 7.2, and so theta is going to sine inverse, right? Sine inverse 1.5 over 7.2. So whenever I solve that through, I come out with 51.1 newtons that I can then substitute. And notice I put my angle that I solved for in for the angle, right, sine of 12.02. So now I'm able to solve for work. So substituting numbers in there, 51.1 for the force, the displacement of the object, I'm pushing it up the length of the ramp now. That's what I'm comparing, going straight up versus the length of the ramp, going straight up versus going up the length of the ramp here. 7.2 meters. And the difference, the angle between the direction it was going and the force I was pushing is 0 here. So here, theta is 0, which whenever you actually multiply all that through and you round for sig figs once again, you come out with 370 joules of work. In other words, if you neglect friction, if you don't have any other non-conservative forces in there, if you neglect friction, ideal ramp, the amount of work you do to go up the length of the ramp is the exact same as if you went straight up the ramp, which proves very, very useful. Now, a ramp is a type of simple machine, and it doesn't mean that simple machines are pointless. Simple machines are very, very useful. Notice what's ended up happening here. My force got reduced, 51.1 newtons, right? But I went a further distance. Over here, though, the force, 25 times 9.81, somewhere around 250, much, much higher. I have to exert a much harder force and go a shorter distance. But naturally, the way the human body is built, it's easier for us to go a further distance with less force than to go a shorter distance with a greater force. That's just the principle of the human body. So while work remains the same as long as you don't have a non-conservative force, it's actually easier to go up the length of the ramp just because not as much force needs to be applied. Now this idea can come in very useful because what this says is that I don't end up having to do all of the stuff with a ramp. All I have to do if I care about how much work is done is pretend that we just lifted the object straight up. All right, lastly, let's talk about graphs. So here up top I have a graph, force displacement graph. An area under a force displacement graph is going to give me my work. So what you do if you have a graph that isn't one continuous function, like here it's a piecewise function where I've got a flat line and then a line going down, is divide it into pieces that are easy to calculate the area of. For example, first piece might be a rectangle, right? That's a pretty easy piece to calculate. And then the second piece over here, I see a triangle, right? And I divide it where I have one rectangle and triangle, and then I add up those areas. So an area of a rectangle, this area here is base times height area of a rectangle. So that's 5 times 2, base of 5, height of 2 there. And then area of a triangle over here, 1/2 base times height, and the base runs from 5 to 7. Had to add in that 7 there because I accidentally didn't put it on. So a base of 5 to 7, 2, and a height once again of 2, so 1/2 base times height. And of course, whenever you do 5 times 2 is 10, 1/2 times 4, 2, so I end up with 12 joules as the amount of work that graph shows between 0 and 7 meters. Now what happens though whenever you have one continuous function, the function is actually given to you? So a certain car's brakes applies a force trying to stop it according to this equation right here to x squared plus 3 when stopping at a red light 35 meters away. So we're going to run this graph from 0 out to 35. And we want to know the area under the curve here. We want to know this area right here. Well, that's the integral, right? And I know work is going to be the integral of f. And since we don't have other dimensions in here, x or anything else, we're just going in the same way, f dx. And I'm going to take this integral from 0 to 35 up here, because that's the area that I'm trying to figure out that stops 35 meters away. This would be an example, kind of odd, thinking about the force increasing because he's pushing the brakes harder and harder as his position increases x. This might be an example where the driver wasn't doing a good job of applying consistent force, started out very, very light, and then realized the closer he gets to the red light, oh my goodness, I better really mash the brakes if I'm going to stop in time. So I'm taking the integral of the force, which was given to me as 2x plus 3 dx to get my work. So first step here, taking the integral here, I'm not going to worry about evaluating just yet. This goes up to x cubed, so now I have 2/3 x cubed plus 3x, and I'm going to evaluate that between 0 and 35. Whenever I evaluate that from my 0 to 35, so final minus initial here, 35 is 0, of course all this completely goes away. I end up with 29,000 joules worth of work is how much work the car's brakes had to do to stop the car. Now, more often than not, you're going to find this type of thing where you need to do the integration whenever you have something that always provides a force that is dependent upon displacement. Cars' brakes aren't necessarily dependent upon displacement at all. It's really dependent upon the human's foot. But we can make it, if we have an equation, we can make it like it was dependent upon displacement. We'll learn other things like springs in upcoming lessons that is dependent upon displacement.